Welcome back to Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we want to show that the derivative of the natural log of x is the reciprocal of x, or x to the minus first power. Now this derivative of natural log of x being 1 over x, this is probably something you memorized all the way back in Calculus 1. You still hold to this day. It's used in all sorts of disciplines, including physical chemistry, which we have in this channel. But what if you're asked to show that this derivative is equal to 1 over x? Well, unfortunately, you can't just rely on power rule, product rule, chain rule, all that stuff. You actually have to go back to the basics and default to the definition of the derivative that you learned all the way back in early Calculus 1. So, if we wanted to find the derivative of natural log of x, assuming this is our function f of x, then f prime of x is equal to the limit as h goes to 0 of, and what we do is we throw an h after this x, so plus h. So it's the limit of natural log of x plus h minus the original function natural log of x, all divided by h. And that's the definition. Although obviously we're not done here. We're going to manipulate this sum using logarithm laws. I can notice that the numerator is the difference of two logarithms with the same base. Therefore, I can combine these two logarithms into one logarithm and take the quotient of the two arguments, which are x plus h and x. So I can combine these two logs into natural log of the quotient x plus h divided by x. All right? And also the other thing I did is notice the denominator is h. I can actually pull that in front of the natural log as 1 over h. All right? Now, why did I go through the effort of doing that previous step? Because if I have some number, anything really, an expression multiplied by natural log, or any logarithm for that matter, I can pull that expression up as an exponent on the argument of that logarithm. Therefore, the derivative is equal to the limit as h goes to 0 of the natural log of x plus h over x raised to the 1 over h power. All right? Now, I'm going to do two things in this step right here. One, I'm going to realize that I'm taking the limit of a continuous function. And natural log, any log for that matter, and exponentials are really good examples where this happens a lot in calculus. Where if I'm taking the limit of a continuous function, that should be the same as taking the function of the limit. Okay? So what that means is I can pull the limit inside the function. And that's what I've done here. So now the natural log of the limit of h goes to 0 of all this to the 1 over h power. Now you'll notice I no longer have an x plus h over x here. I have a 1 plus h over x. How did that happen? Well, I distributed this x in the denominator to both the x and the h. So x divided by x is 1, and then h over x is h over x. All right? Now, before I go any further, unfortunately I have to do some other technical things over here that have to do with the irrational number e. Now, if I look at this limit inside the log function right here, the limit that I just obtained, it looks a little bit similar to the definition of e. The definition of e, for a reminder, is the limit as t, which I'm using a different variable to avoid ambiguity, the limit as t goes to infinity of 1 plus 1 over t raised to the t power. That limit is e. Now, I'm saying it's awfully similar to this limit in here, but there's a few problems, and they're pretty obvious. One, the h is going to 0 here, whereas t is going to infinity. Very different limits. I do have a 1 here, but notice I have h over x, so h over the variable. Here it's just 1 over the variable. And then I have a reciprocal exponent, 1 over h, and here's just a regular one, t. So it's a little bit similar, but it looks very different once you actually take a closer inspection. What I can do, though, is I can transform this limit in the following way. I'm going to do a u substitution. I'm going to define u as being equal to 1 over t. So why do I do that? Well, I have a 1 over t right here. All right? So 1 over t I can just replace with a u. So you see the u right here. Also notice, if I were to multiply both sides by t and divide by u, I could obtain an expression from here that t is equal to 1 over u. So I can replace this t with 1 over u, all right? And also let's take a look at the limit. I'm letting t go to infinity, so if I evaluate this expression, u equals 1 over t at infinity, t is infinity, so 1 over infinity is 0. So as t approaches infinity, u should approach 0. So I can actually change the limits to u approaching 0, and since all I did was a u substitution and I accounted for all the variables, this limit is still equal to e. Alright, so the limit as u goes to 0 of 1 plus u to the 1 over u power, this is still e. And now I have something that looks fairly similar to what I have here. I now have a reciprocal exponent. I have a limit that's going to 0. The only problem is I still have this h over x. So how do I deal with that? Well, let's say this u that I just found from this limit of e right here, let's define it again. Let's say this u is equal to h over x, which is actually fairly reasonable because this 1 plus u, this u is the same u, or it's the same part of the expression that is this h over x. They correspond to each other, okay, or at least they would seem to. So let's let u equal h over x. Well, let's think about it. If h goes to 0, so it's 0 over x, u should approach 0, so still makes sense. But what I can also do is I can multiply the x up on the u, and I get this expression h equals u over x. Alright? So what I'm going to do is the following. I'm going to replace this h over x, since I'm making the u substitution, replace h over x down here with u. Now, I'm going to replace this h in the denominator of the exponent, this h, as ux. So instead of being 1 over h, it's going to be 1 over ux. So let's regroup. What is my derivative now? It is the natural log of the limit as u goes to 0 of 1 plus u to the 1 over ux power. Okay, this seems not complete yet since I still have an x here. I'm not evaluating x, I'm evaluating u as it approaches 0. So I need somehow to get rid of this x. Well, I'm not really going to get rid of it. What I'm going to do is I'm going to use exponent laws. This, if I were to say 1 over ux, that could equal 1 over u times 1 over x. And since I can technically break the 1 over u and the 1 over x into different fractions, I can actually pull the 1 over x as an exponent outside of the limit, right? Because if I can multiply these two fractions together, these two exponents, and get back to 1 over ux. So I can pull the 1 over x out behind this parentheses. So the first derivative of f with respect to x is the natural log of the limit as u approaches 0 of 1 plus u to the 1 over u power, and this limit is raised to the 1 over x power. Still haven't changed its value. This is a really good thing. The reason being, this limit that's basically being raised to the 1 over x power, that's e. So, I can take away this entire limit now because I know what its value is, and say that the first derivative of f with respect to x is the natural log of e to the 1 over x power. Now, this is easy to evaluate because natural log and e are inverses of each other and they effectively cancel, leaving only the argument of the exponential function. So, natural log of e to the 1 over x is just 1 over x. And that is proving that the derivative of natural log of x is 1 over x. Now, there's another way to do this with implicit differentiation, which I'm not going to do in this video. But the reason I'm doing this method is because, first of all, it involves the basic definition of the derivative, and using the implicit differentiation technique, you also have to know derivatives of the exponential function, which those aren't necessarily intuitive. You pretty much just memorize those, right? So this method bypasses any need to know derivatives of exponential functions or derivatives of natural log functions. So you can actually prove this derivative without really any calculus other than the initial definition, and everything else is pretty much just limits and log and exponent laws. Alright, so hopefully you learned something in this video. Please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.